similar to the chapter 22, we need to calculate quite a lot about the potential for different cases like charged particle, electric dipole, continuous distribution, blah blah blah, and yeah, and yeah, we will also introduce another uh, variable called the potential energy, which is related to the electric potential. And yeah. So now we define another variable called the electric potential. We use the letter V to denote it. So at electric potential V, the electric potential V at the point P in the electric field of a charged object is like this. So it's somehow similar to what we defined the electric field in chapter 22. So in chapter 21, we learned the electrostatic force, the Coulomb force, F equals to 1 over 4 pi epsilon naught Q1 Q2 over R squared for two charged particles. And then in chapter 22, at the very beginning, we learned the definition of the E field is the electrostatic force divided by the test charge. And now, similarly, we define the electric potential by the energy and the test charge. So the U is the potential energy if you put two charged particles in a finite distance, because they should have some force to push them away. It's somehow like if you jump up, the earth will attract you back. You fall down. You just jumping, then you fall down eventually. So you should have something like the potential energy, not the electric potential, but the gravitational potential. So here we have the electric potential U divided by the test charge Q0, and it will be the electric potential. So that this V does not related to the test charge itself. It only consider how large the E field or the electric potential generated by some sort of charge distribution. And you can consider you need to do some work so that you can put two charge together, maybe a positive work or maybe a negative work done. But it has a negative sign here, so this is the difficult part for the physics usually, because when you need to consider whether you need to put a negative sign, it will be very tedious. It will be very tedious, and then you need to solve. So actually, here are many equations, but actually similar to what you have learned in the mechanical system. Is somehow like the delta of kinetic energy. The kinetic energy is somehow like the conservation of mechanical energy. In mechanical system, you have kinetic energy plus the potential energy will be the total energy. If there is no loss within the system, then the mechanical energy will be conservation. We conserve. And usually, what you learn is the conservation of momentum, because it doesn't really matter whether there are a loss for maybe some collision of two objects. Then you can usually use the conservation of momentum. But when you use the conservation of mechanical energy, and then you need to verify that whether there are any energy loss in between. So we will have somehow like the change of the kinetic energy is the negative change of the potential energy, and which is nothing special. The only thing you need to consider is, or rather there is a negative sign there. So here is a sample problem. Here's the same sample problem. So electrons are continually being knocked out of the air molecule in the atmosphere by cosmic wave particle coming from space. 就是在外太空有一些高能射线，就会把那个大气层的一些就是氧气的原子把一些电子射走就是所谓的电离的现象。So once released, each electron experiences an electrostatic force due to the electric field that is produced in the atmosphere by changing particles already on Earth. So near the Earth's surface, the electric field has the magnitude E and is directly downward. Directly downward. What is the change delta U in the electric potential energy of the released electron when the electrostatic force causes it to move vertically upward toward the distance d? Through what potential change does the electron move? So this is actually a phenomenon in the natural world, but it's simplified to a very simple physics model. So it assumes there is a constant E field directly downward, somehow like this, and we assume there is a electron, and then it tries to go upward through a distance d like this. And then through what potential change does the electron move? So it moves like this, like this. So actually you should know that the work the electron has done is somehow like the force inner product with the distance vector. So actually you should have learned it in a mechanical section. And in chapter 22, you know that the electrostatic force is nothing but the Q times the electric field. Q times the electric field. So here Q is an electron, so it is a negative charge. It's a negative charge. And you can imagine if you place a negative charge in an E field pointing downward, it should go upward. So the work done by the E field should be a negative. Should be a negative value. So it will be negative E no. So it should be wow. It should be somehow like so it should be Q. You can see that E and D are in opposite direction. So it should be ED cosine 180 degree. So it would be negative QED. And suppose you substitute Q would be minus 1.6 times 10 to minus 19, which is a elementary charge amount, and E is 150, and D is 520 meters. So you can find that the work is 1.2 times 10 to minus 14 joules. And the potential energy delta U should be negative minus W, which is minus 1.2 times 10 to minus 14. So this one should be a negative value. You can simply imagine that if it is a gravitational case, so you can imagine this is the floor, this is the floor, this is the floor, and then if an object is placed or at h equals to 0, it has the smallest potential energy, right? And if you just put it here, then it should fall down spontaneously. So and actually you can see that the potential energy here should be mgh, which means that the delta U should be, this one should have no potential energy here. So the delta U should be 0 minus mgh, which is negative mgh, which is a negative value. And here is the simulus case, which is if you place a negative charge here, the E field onto this side. If it is a positive charge, it should go this way. If it is negative charge, it should go this way. So in this case, the delta U should also be a negative number, similar to that case. Yeah, so actually it still asks you through what potential change does the electron move. So actually we also need to calculate delta V is delta U over Q. So you can just plug in minus 1.2 times 10 to minus 12, not 12, 14, and then divided by minus 1.6 times 10 to minus 19. So the answer will be 4.5 times 10 to the fourth power voltage, which means 45 kilovolt, 45 kilovolt, which is 45000，就是比卡丘的一半，差一点点。So next we talk about the equal potential surface and electric field So it will be related to the electric field line. Or if you will learn somehow the differential geometry or multivariable calculus, you may learn some math related to this stuff. So actually, electropotential surface is adjacent point that have the same electric potential from an electric potential surface, which can be either an imaginary surface or a real physical surface. So you can just imagine in a map you have you can maybe you check on the Google map, you can see the electric height line, so that you can have something like this. Maybe so you can imagine, you can check on a map. If there is a mountain, you can see somehow like this, 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 this. And maybe there's another mountain nearby, then it will be somehow like this. Then you see that you can know that this one is the highest point and this one is the highest point. And every point on the same line should have the same height. So it is the what you can see an analogy when you check on a map. And here for EM theory or electrostatic theory, we will say this one is the equal potential surface。中文应该叫做等式面啊，这是啊，中文我很少去。So actually, equal potential surface. So figure shows a family of electric potential surface, and the work done by electric field on a charged particle as the particle moves from one end to the other end, path 1 and 2 is 0, because both ends for the path 1 are on the same surface, V1, on the same equal potential surface, V1. So that, of course, the work done for this movement is 0, because delta V is 0, so that the W should also be 0. And for path 2 is this one. Path 2 is this one. So you can see that this point is going outside, going somehow like to the V4 and then go back. But actually it only cares about the starting point and the end point, or the destination point. So so the delta V here also be 0. So the work done for this movement is also 0. And of course, path 3 and path 4 is not 0, because it's go from V1 to V2, V1 to V2. But for path 3, it directly from V1 to V2, and then for path 4, it go a bit to actually maybe V3 and then go back to V2. But actually, it only care about the two endpoints. So the endpoints are V2 for both and V1. So the work done are the same for path 3 and path 4. They are not 0, but the work done for these two charge movements should be the same. So mathematically, we will write it as an integral, because not all the same time the E field would be uniform. So if the E field is not uniform, then we need to express it in integral form. So here the potential, electric potential difference between the 2 point I and F, initial and final maybe. So Vf minus Vi should be defined as E dot ds integral I to F. Because just now we will write it as yeah, the work done is somehow like uh, F dot ds I to final, and then we will have uh, yeah. So I'm not sure whether to stop or W or U. Maybe it should be U. It should be U. It should be U. U in this case. Yeah. So we have no. It should be W. 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 W is the work done. And then the potential energy change should be negative W. So then we have a negative sign there. And then finally, V should be U over Q. Rare? Yeah. Yes. So we have somehow like minus integration I F. Here F should be Q E dot ds. So Q and Q cancel. You already. Okay. So it's somehow like that. So we have the V have an expression like this. And actually, we will write it as a electrical. Yeah, if we choose Vi to be zero, we can simplify the left-hand side to be a simple V like this. Simple V to be negative of the integral of E field over a path, path. So it's somehow like a line integral. Line integral. Have you learned the line integral yet?冇教。你接觸咁多嘢。So you can imagine in single variable calculus, you have f(x), f of x, and then you dx from a to b, somehow like this, which means that you integrate this f of x over a given path, which is from this is x. So this is A, this is P. So you can imagine in a three-dimensional space, this is Y, this is Z. And you can just fix Y to be 0. You can just fix Y to be 0. So this point is actually A0, E0. And you can regard it as a special case of a line integral. So now the line integral can be different. So you can suppose you have a line on the xy plane, on the xy plane. So this is somehow line f of x, y. Or maybe a field. There are two different cases. Actually, maybe I just go to the vector form. Maybe, yeah, maybe I just use the scalar form. Maybe easier to explain. So this is the direction. So another a function f defined on xy so that it should give some number. It should give some number. Maybe you can just put in x to be 0, y to be 0. That should be a number. And then if x is 1, y is 1, that should be another number. Now we define a line on the xy plane. And then we try to calculate this one, fxy d, maybe dl, depends on what you like. Maybe this line is called C. And this is the starting point, this is the end point. Then you can imagine you just cut it into many parts, and then you try to add this part, and all of them add together, and then it is the line integral. And here it will be a bit more complicated because it involves the vector notation. So that for every small step, we need to consider the field here, E, and then we inner product with the tangent line at that point, Somehow like ds should be the tangent line at that point. ds should be tangent line at that point. And then we calculate the inner product, and then we add all of them together. And this is the line integral up here. And of course, if you have, I suppose you should have learned this in high school, because if you haven't learned calculus before, then we really need to talk about the electric field or the electric potentials. Then you will assume the E field is a uniform E field, and then you can just make a complicated integration to be a simple multiplication. So actually, for electric potential, the SI unit should be volt. I suppose all of you should be familiar with, because you have learned the circuit analysis. So the SI unit for V should be volt, and in this case, the SI unit for E, the electric field, can also be written as V over M, because this is V, this is M, so this can be V over M. So then you can either write N over C or V over M, which are also correct. So this is a special case. If you consider for a given path which has a constant E field, then you can simplify this one into a simple multiplication, which is nothing but the E field times the delta X and with a minus sign, which is the delta V. Okay, so let's have a simple sample example. So 2 point I and F in a uniform E field. The point lines on the same electric field line not shown are separated by distance d. Find the potential Vf minus Vi by moving the positive charge Q0 from I to F along the path shown. which is parallel to the field direction. So we can see the E field pointing downwards, and initial point is here, and the final point is here. So it is moving also downward, and it is a positive charge. It's a positive charge. So you can imagine the potential is this side is higher and this side is lower. So you can see that if you use the VF minus VI to be, if at the very beginning you don't really familiar with it, you can try to write more concretely so that you will not get lost. So it is somehow like I to F E dot ds, E dot ds. And you can see that ds is pointing downward because this line is from here to there. So the tangent line is have the same direction from I to F. So ds is pointing downward, and E is also pointing downward. So this is a positive number, and overall it should be a negative number, ED. Which means that VF is the potential electric potential at this point, and VI is a electric potential at that point, and VF minus VI is negative. This one is negative, which means that this one is higher, has a higher electric potential, and this point has a lower. And you can also remember this fact is that the potential electric field is like this, so that this sign has a higher electric potential. This one has a negative sign. If you are very good at math, you can just know this fact by observing this equation actually. So for part B, so actually this is still D. This is still D. And it tried to go in another path. Try to go from I to C and then go to F. So actually for the previous case is directly go from I to F. Now we try to calculate the voltage difference VF minus VI by I, C, and F. And actually it should be the same, but it's another example to show you if you don't really believe that one. So first we try to calculate VC minus VI by minus I to C E dot ds. So E point to downwards still, and ds from I to C should be pointing to the right side. So ds. So they are perpendicular to each other, which means that the inner product for them should be 0. So this one is 0, this one is 0. And for the next step, we calculate VF minus VC. So ds is pointing this way, So we have negative integration from C to F E dot ds. So E is still E, and ds actually the total distance moving from this one from C to F should be here, should be square root of 2D square root of 2d because this is 45 degree. So this side and this side should be the same. So this is d, this is also d. And then you use the Pythagorean theorem. So you know that this side should be square root of 2d. So square root of 2d, but you don't forget the term for the inner product. You need to have e times this one times the cosine theta. Cosine 45 degree is uh, square root of 2 over 2. So finally it will become minus ed. And so when you add these two together, you have Vf minus Vi equals to minus Ed. So that it doesn't really care about the path you go uh, from I to F directly, or go from I to C and go to here. Or maybe you go like this and then finally come to here. But actually this only adapt to the electrostatic case. If there are some magnetic field, things will be different.